Hi, this is Sohel Selki, and I'm doing a quick video to introduce the different data path elements so that they can be recognized in later videos. I won't be demonstrating the different parts working, nor will I be explaining how they work. I'm just going to quickly cover them, point them out, so that you can follow along in the later videos. Alright, so getting started, in this orange area here, this is the program counter. You can see that it's labeled PC. You can also see that it is carrying information. Right now it has the value of 3 loaded into it, and the next time it iterates it will show 100 for 4. PC has 2 outputs. It will either output to the ALU to calculate changes in the PC, or it will output to instruction fetch over here. On to instruction fetch. Instruction fetch takes in 5 bits from the program counter, 5 bits for 32 possible instructions, which are encoded here. Instruction fetch will then output a 7-bit instruction to the control unit. You will see that there are actually 8 bits coming out of here. The last bit is for a function that is not currently implemented. It was put in as a flag bit to either turn on or off a fully automatic run mode for the processor, but it has not been done yet, so we're only concerned with the first 7 bits in this line, which will bring us to control. Control is a fairly complex unit because it sends bits everywhere. You'll also see that there are signals that travel out, color-coded here in this purpley color, which turn on and off certain muxers or functions within the processor, essential to doing certain instructions. I will quickly explain what these buses are and where they go. These 3 go to the memory unit to select one of our 8 memory locations to either read from or write to. These 5 will go for immediates, branch not equal 0 and add immediate, straight to the ALU. And these 6 down here go directly to the register. These 6 are actually 3 different fields. The first 2 select what we are outputting on output 1 for the register. The next 2 are for output 2 on the register, and the last one is what register we are writing to on our input to the register file. The register is here outlined in red. You can see that it is labeled. There are 2 outputs on the register file. On output 1 here, it will go straight to the ALU for computation, and on output 2 we will either go to the ALU or to memory for storage. You see here that the register are 8 bits wide, and these are them: 1, 2, and 3, and 1, 0 register, which is not physically implemented because it returns nothing. There is a selector here to determine whether we are sending to memory or to the ALU. Once all input bits are sent to the ALU, a user will have to engage it to have it calculate the output. The output is then sent here, awaiting to be dispatched. All outputs from the ALU get directly to the register here and await being written for the write back phase. This is the write back button, which will write any bits that are sent here. Write back is done automatically at the end of a cycle, but this is a button that will trigger it early. While we're here at the register, I will discuss quickly a memory write. On output 2, if we send out something to be written to memory, we will mux this. This is normally closed, but when we get a signal here from control, all of these will close and we will have no contact here, and our signal will be sent down to the memory unit. This is memory input on the bottom and memory output on the top. Once we've written to and read from memory, the bits will be sent along the top here back to the register to be used in any other calculations. You may notice that this could possibly travel this way if you're unfamiliar with Minecraft, but these are repeaters and they're unidirectional. Any repeaters, if you can see that arrow, it's pointed this way, prevents any sort of signal from traveling in this direction. So all of the signals that come down to this point will only go towards the register file over here and sit there awaiting write back. The last and also the first element in the data path is our program counter. At the end of a cycle, the user needs to signal the end of a cycle by pressing that button there labeled next cycle, which will cause control to send a signal to the program counter. Program counter will then release any bits that it has stored here to the ALU. The ALU will be given a signal to have a carry bit, one of the inputs that we also use for subtraction, and it will add 1 to whatever is in the program counter. In the case of a branch not equals 0, it actually functions identical, except that we will have an input on input 2 of the ALU to add to our program counter. A control signal is also used to select an output for the ALU. This isn't really a true output. This is not really serialized. It just feeds directly into the program counter. So the bits are released, the calculation is done, and after a few seconds, all of these will flip over and the output will be sent directly into the program counter, instead of coming out through the normal path which goes to the register. That is all of the data path elements and all of the buses that send information to different places. I will go over them one more time. Here in the orange is the program counter, which sends to instruction fetch in the yellow. Instruction fetch will send a 7-bit instruction to control, which will handle any other control bits that need to be sent out. Control will either send information to memory to select a memory slot, to our register for moving functions and virtually every other instruction, or if it has an immediate, it will send it here to the ALU. Here in the red again is our register. Over here in the slightly pink color is our memory unit with 8 memory locations. Here in the green, hidden beneath a tangle of signal wires and control wires, internal logic, is our ALU. And lastly, we are back to our program counter.